Set, I hope. Fantastic. Okay. This presentation is going to be pretty practical. I'm going to be discussing mainly the monitoring aspect of directly monitoring audio over IP. And of course, by now you've got an excellent overview of how different standardization things connect together. And I don't have to say too much about that. I'll be going through a little bit of the same material as Andreas was showing earlier. But if we look at where we are coming from, the traditional way of getting connected means that you have special cables installed usually by special people who know how to do this for audio, whether it's analog audio or the traditional digital audio in the form of AES, EB or similar. You need a dedicated cabling that is not the kind of standard that is used by any odd electrician who's installing cabling. So you have to know what you're doing, and you need dedicated cables for every single audio feed that you're running. So in this example here, the audio is coming in, going out, and we need two cables to do this. But it doesn't obviously stop there. So if you want to monitor or control your devices, then you need usually additional connections into the devices, additional cables. So you end up in a system that's pretty complicated. And this, of course, is one of the areas where the doing everything over IP really becomes a great benefit, has a great potential of helping things. And the traditional way of doing things is pretty messy. Let me do a quick comparison here. Let's look at the old method against the new method. So if we look at the new method, then we are using standard cabling. So the standard IP cables are the standard cables going into every building today. So all the electricians know how to install IP cabling, and they know how to do it properly. They usually get it to work okay. So this is a great potential. It's actually very valuable, and also this means that installing the cable is going to cost you a lot less. IP technology has very long lifetime. I mean, we are coming out of maybe 4 decades of development, where the developments usually are somewhat more or less backwards compatible. So you have a great security for investment in this area as well. If you compare this to the traditional audio way of doing things, then usually you get the new generation of devices that is not compatible with the previous generation of devices, and your previous investment is lost and you have to reinvest. But with IP technology, you have certain security that usually doesn't exist in the traditional audio way of doing things. If we think of one of the key benefits of IP technology is that it's agnostic to the signal that we are carrying. And this is very important. So we can stuff any kind of signal fundamentally in IP network, and the network will be able to deal with that. It will be able to carry the signal. So as long as you have the software in place, the signal can be carried. In terms of audio signal, this means that we don't have any limitations in terms of the clock rate, the word length, the format of audio, the number of channels, and many other things that usually are a great limitation for the traditional way of building audio connectivity. Andreas, I think, made a very good point that we are using standard protocols, and we also have standards in place enabling different devices from different manufacturers to connect together over IP networks. And I seem to be competing with the other stand over there, so I hope you can hear what I'm saying. But anyway, and this is excellent. This means that the future is probably going to be brighter than where we are coming from, because we will have easier connectivity across different devices from different manufacturers, and again the security for investing in the new technology is very high. Also the IT-based technology, the networking-based technology is low cost to maintain, and this is another important aspect in all of this. because the network is agnostic, it means that everything can be carried over the same network. You don't have to be building separate networks to carry control, monitoring, signaling apart from the audio. And this simplifies things tremendously, and it actually enables easy connectivity in an entirely new way compared to how things were done in the past. If you think of how to get connected for audio over IP, then we have maybe 3 different methods of dealing with this. You have dedicated equipment that have usually a pretty high number of inputs and outputs. This is usually a relatively expensive way of getting connected, but it's certainly an effective way of doing so. Then you also have the possibility of using adapters that can convert your existing equipment to have the capacity to send or receive audio over IP. And then, of course, increasingly in the future, you will have devices that can directly connect to IP networks and can send and receive streams of audio over IP. If you think of the monitoring, minimum configuration for monitoring audio over IP, then the central part of all of this is the IP switch. So this is where everything gets connected to. We of course need a source of audio. It could be a computer, some other audio workstation. The key aspect usually here is running the correct software, and the hardware level of connectivity to IP is entirely standard, so you don't need any special hardware devices between your IP switch and your workstation. And then of course we need a sufficient number of loudspeakers to deliver the number of channels for our ears. On top of this, you usually need a Clockmaster device on the network. And this is very important because it actually, and I'll come back to this in a moment, this device makes sure that all the devices on the network understand the absolute time exactly in the same way. Luckily today, increasingly, the devices that are able to deal with audio over IP streams are also able to act as PTP Clockmasters, and this means that in most of the time your minimum configuration doesn't actually need this PTP Clockmaster device. That this, what you see on the display at the moment, is actually your lightest possible audio over IP monitoring system. The important point to make here is that there are no usual limitations that you would assume to have in an audio environment. So for example, you don't have any absolute limitation to number of channels that you'd be able to reproduce. So all you have to do is you have to bring in more loudspeakers, get them connected, and you're in business. And the PTP clock synchronization will take care of synchronizing all these different devices so that you can create a coherent, properly working audio image. I'll come back to that in a moment. The networking standards are developing, and they have already developed to a very good level. We have the traditional audio over IP operators that didn't used to be compatible with each other, but with the advent of AES67 and ST2110, we now have interoperability, so that you can make devices that have been built for these different ecosystems talk to each other and work as a single system. And we have this standardization work going on at the moment to improve things for the future. In fact, AES67 becomes very central in all of this. As Andreas, the previous presenter, was explaining, it's actually the key for the upcoming standards. So it's kind of existing in the standard developments. So getting to know AES67 is a very worthwhile investment for all of you. For those who has been reading the standard so far, have you downloaded the standard documents? Have you read it? If you haven't, I think I would recommend doing so, because it's actually very good reading. It's a very logical explanation of how audio over IP works. It will walk you through all the different components that you need in running this kind of system. So it's actually very good reading to go through this AES67 standard. There's a lot of support in the industry for this this development at the moment. Here are just some of the names that would be relevant in this area. And these are the equipment manufacturers, but the other side of this are the broadcasters, the people who would actually be using these devices, and there's also great support for this technology there. Something that's also very good reading is the EBU, European Broadcasting Union documents. Those are freely downloadable, so if you want to read them, just go to their site, download the documents, and they are freely accessible. One of the key aspects that EBU, for example, is advocating at the moment is this concept of technology pyramid that the previous presentation also quickly showed. At the top they have the media transport service there, but they are also kind of trying to make the point that you need some other very important layers in all of this in order to make the whole audio over IP, video over IP, media over IP networking work in a reliable fashion. The other layers that they recommend that they advertise are the time and sync related aspects, and there of course the PTP version 2 is central at the moment. Discovery and connection establishing standards, configuration and monitoring for devices, and then finally, and maybe most importantly for wider area systems, security aspects, so that you know that you're talking to the actual devices you think you're talking to, and you know that you're taking commands from devices that you should be listening to. So in order to make sure that your overall system consisting of a lot of devices is working in a reliable fashion. If we think of what AES67 covers of all of this, here is the subsection that is covered by AES67. Let me flick back and forth a little bit here. So if we look at the whole technology pyramid, we would be looking at this set of things, and if we then bring in the AES67 covered areas, we would have these aspects covered. So you can see that some of the aspects have been standardized elsewhere, such as ST2110, and the work in those areas is going on as we speak. So let's go back to the monitoring of audio for IP audio. We have different and increasingly complex loudspeaker layouts that we need for monitoring audio. So we come from the traditional two-channel stereo, then we have the single layer surround systems, very heavily used these days, and we are increasingly moving to immersive multi-layer audio systems at the moment. So when we consider monitoring to audio intended for this kind of system, it means that we have to be handling the virtual sound images carefully. For the standard single layer stereophony, we have the sound stage, and we are creating these virtual sound images usually between two loudspeakers, and this works for everything from the two-channel stereo upwards to any number of channels in a single layer. When we go to immersive audio, then we bring in additional layers and we start creating virtual sound images also in the height direction, not only on the horizontal direction. And the key here is the virtual sound image, and taking care that this is being created in a reliable fashion. It means that we have to fulfill certain assumptions about how this kind of system is configured to work correctly. Some of these assumptions are usually that all the loudspeakers in this kind of layout are at equal delay from the listening location and are reproducing the audio at equal level for the listener. In order for us to fulfill this, then we have to keep in mind that the individual loudspeakers in audio over IP reproduction systems are totally independent units, and the network itself it doesn't take care of making sure that these devices would be belonging into the same set intended for reproducing a certain audio presentation. So we have to bring in additional tools, the key tool here being the PTP clock synchronization, in order to make sure that the sound image that we create here is coherent and is working correctly. The traditional way of dealing with this is a lot easier, because usually what you're doing is you have a single device, and that device is actually feeding all the loudspeakers. So your synchronization can be handled easily, because it's kind of already covered mostly by just the simple fact that all your channels are originating at this one device. If you don't have this situation and you are actually feeding independently multiple devices, providing signals for your loudspeakers, then you may have to synchronize your devices. For example, in the traditional way of doing this is to use house clocking. The house clocking doesn't establish absolute time reference. It does create you absolute frequency reference, and that's of course important. But in order to make sure that all our loudspeakers are phased correctly to create the sound images correctly, then we have to make sure that we also have absolute time implemented correctly. And we may have to adjust certain devices here in order to bring to make sure that the delays through the different audio paths are the same, so that everything gets delivered correctly. The audio over IP standard actually has a similar notion implemented as part of, for example, the AES 67. They talk about the synchronized mode. The synchronized mode is working similar to the house clock. It doesn't guarantee you absolute time coherence, but it does guarantee you that the frequency, the sampling frequency, is precisely the same in all devices. So this mode is working similar to your traditional house sync. What we would like to have is the absolute time being correct. And this we can have by bringing in the PTP synchronization. And then this actually ensures that all these different devices have correctly and exactly the same understanding of the absolute time. So that when these devices play out audio, it's happening at exactly the same moment of time. Everything is in phase and in sync, and we can create correctly the sound images. The other aspect to look at when you consider audio over IP is the delay over the network, and this usually creates a lot of discussion in professional circles. So if you consider audio over IP networking, then we have the concepts of ingress time, so when we put the audio on the network, and the egress time, when we take audio out of the network and we provide it for the device locally. And there are a couple of buffers needed in order to just get the audio data on the network and out of the network, and it's shown as buffers in this conceptual image here. And what the key concept that we are dealing with is the link offset, because link offset is now an amount of time that we need in order to pass audio through the network and to the receiver. Let's take an example of this. We start with the microphone, and then we A to D convert audio. It takes a bit of time. Then we have the audio data. We can start stuffing audio data into IP packages in order to send it over the IP network. And we do that, and we then send the packet at the ingress time. Depending on your operating environment, you may have more or less additional delay happening because of, let's say, operating system functionalities. If you're running a software-based transmitting system, so there are variations in this area. And then you spend just a little bit of time passing the physical data over the network to the receiver. This usually is not a very long time. Then at the receiver, at the egress time, we take the packets out of the network, we bring them into the device, and then we unstuff the packet, we take the data out, we process the data, and then we can play the data as audio. And this is now showing you the total amount of time needed in order to pass audio into, for example, a loudspeaker to be played out for your ears. And AES 67 standard is describing how these different concepts related to delay link together. And I'll just show you a table that comes out of the AES 67 standard, where you can see on the left column the packet time. Packet time is the amount of amount of audio that you can stuff into a single IP packet. So, for example, the standard requires that everybody's implementing 1 millisecond of packet time, so that the packet is able to accept 1 millisecond of audio that you can then send in the packet to the receiver. And this then implies a certain minimum link offset and maximum link offset in the network. So the offsets are related to the amount of time that must pass before you can take the audio out of the network and play it. Related to this concept is the concept of presentation time. When you are putting audio on the network, you then have to use a little bit of time to pass the audio to the receiver. And if you desire to present the audio after a given delay, for example in a loudspeaker, then it must happen after the minimum possible link offset time. If you are requiring something very stringent and it's actually less than the maximum link offset that possibly the network would have to spend, then there's a possibility that some of the packets are coming in too late and they are not presentable. So when you receive the audio too late, the point in time when you intended to play the packet is gone, so you have nothing to play. So this is the typical reason why people can be frustrated at some point of time with audio over IP networks, because they get silence out of the network and they wonder why this is happening. And this is one of the reasons why this may be happening, because you require the network to be working kind of too well, to be too efficient in delivering the audio to the receiver. In order to deal with this, you have to consider how much audio you stuff in individual packets, because you can only send the packet off to the network when it's full. But if you decide to put less audio into each packet, you can send it off earlier, so you can spend less time sending the audio into the network, and also less time receiving the audio. So these different concepts are linked together, and you would have to consider them when you are setting the desired presentation time that you want to use on your network. Finally, Ethernet offers us interesting new possibilities. Of course, the time synchronization, that's fantastic. The agnosticism to the data that you're carrying is also fantastic, because you have a great degree of freedom in using the network. And one of the additional possibilities is power over Ethernet. And it's of course, you know that it's widely used already by different kinds of equipment, but it could also be used in devices like loudspeakers. And we actually are running a pair of loudspeakers on the Genelec stand that are applying this principle. So what we have is a single cable connectivity on the IP network, and that single cable is now carrying everything. It's carrying audio, it's carrying the monitoring messages, control messages, and it's also carrying power into the device. So IP networking enables this, so we can have this wonderful situation where you only need one cable to do everything, and then that simplifies matters even more. In order to do this, you have to know how power over Ethernet is working. What you are provided is a constant rate of input. Here you can see 4 different power levels that have been standardized at the moment for power over Ethernet. We start with the standard PoE at 13 watts into the device. The currently very well available level is 25 watts into the device, and then you have a couple of higher power levels that have been standardized that you can buy into, but they are maybe not so widely being used at the moment in the industry. So what you have is a situation where you have a constant rate of power input into the device, but if you are working with a signal like audio, then you know that audio on average has a relatively low power level, but then you have very high peaks. You know, depending on the crest factor in your audio, you can have very high peaks, but your average level is relatively low. So you need a local power supply in your loudspeaker that enables you to reproduce these high power peaks and without being limited by the capacity of this PoE network, so that you can live with the dynamics that you typically have in audio signal. You can deliver the high peaks, and you can still accept power into the device through the Cat5 cable at the constant rate that is possible for the cable. Okay, so this new technology is looking very promising. It's enabling a lot of things. Let me just finalize the presentation by showing you some case examples of applying audio for IP. The first example comes from the BBC project studios. BBC has done a wonderful work in bringing all the equipment in the studio to work over IP. Swedish Radio is doing similar work at the moment. They actually have transformed local radio studios to do everything that they do, including contribution from the field over IP using standard technologies. And they also have been doing a lot of work with the user interfaces that are being used to control and drive these kind of systems to enable normal operators do this work when they are just doing the program. You have increasingly implementations of the virtual radio studio concept, which is basically a radio studio mostly being just software, using standard equipment, standard IP, networking technologies, and really enabling totally new ways of doing radio and I suppose also television in the future. People are being educated to do this. This example comes from the a university in Utrecht in Europe, where this again is a studio where everything is working over IP, including audio, of course. This technology is very good for mobile applications, and the next example comes from China. This is a portable studio. This is a TV studio. It's supporting stereo and surround audio as well. You can see the audio for IP loudspeakers spread through this TV monitoring space here, and everything is connected over IP. This means that the up and down time of this, when you transport this into a location and you build it up, the building time is very short because you just get cables connected, you put devices in place, and then you just configure everything to work through using a computer. So this, I guess, is where the world is going, and that is very nice. And of course, we reap some benefits in the AV install as well. This is a public venue, a church, where distributed audio has been implemented with audio for IP technology. This is very nice because the control, what signal you drive into the loudspeakers, what level you use, how you use the loudspeakers, it's all software at this point, because you are using IP technology. Everything's happening over IP networking. So in situations like in this kind of restaurant, this restaurant is in northern Finland, and this was actually our first audio for IP loudspeaker implementation. It's running something like 45 loudspeakers straight through the restaurant here. And now you have totally complete freedom. You can zone up this space. You can decide what you are feeding into the individual zones, how you are using this. Are you running signal from a microphone, or are you running from some kind of audio stream, some background music, or whatever you want to do? Things become very flexible. So this was a very quick overview of what you can do when you are moving to media over IP technology for audio. Thank you very much.